Okay, so we had used in the proof of the convergence of the EM algorithm the concept of information theoretic divergence, and we had used the fact that it is always sort of non-negative. So let me do a quick sketch of the definition and the non-negativity property now. So we call it information theoretic divergence, or we call it Kullback-Leibler distance, KL distance, and this quantity, and I'm only going to write it out for in my notation for a discrete random variable when I actually write out the full expression. But this first definition that I'm going to write out, it's that it's the expected value under the distribution P of the log of the ratio of the density of P to the density of Q. That generalizes to continuous random variables and vectors as well. So this is the general definition of KL distance or information theoretic divergence. And for my notation, it'll be, for doing the proof, it'll be easier to just talk about discrete random variables. So how do I do this expectation? Well, I sum over all x. I weight by the probability mass function evaluated at x, and I write out the function whose expectation I am evaluating, right? The ratio of the probability mass functions of P and Q. And the result we used in the convergence proof for the EM algorithm was that this divergence is bigger than or equal to 0, regardless of the choice of P and Q. And we also noted that equality in this happens if and only if, and this is what we often denote by IFF, P is the same as Q. For discrete random variables, basically that means the probability mass functions are the same for all x. For continuous random variables and vectors, the probability densities are equal almost everywhere, basically. So that's a concept that you may or may not have come across, but that's basically means that pretty much everywhere that you have non-zero probability, the two densities are equal. So the proof of this result is actually remarkably simple. It relies on the concavity of the log function. So let's draw the log function. Log is 0 at 1, at x equals 1. And it's a concave function like that. And at if I'm looking at x tending to 0, log is going off to minus infinity. So this is log x. And pretty much a defining characteristic of concave functions is that they always lie under any tangent to that function. And I'm interested in a very specific tangent for this proof, the tangent at x equals 1. So what's the slope at x equals 1? It's d log x by dx, which is 1 over x, and this is 1 at x equals 1. And of course this log function is 0 at x equals 1, so this tangent, this line has equation x minus 1. The slope is 1 and it vanishes at 1, right? And the very simple observation here is that x minus 1 is bigger than or equal to log x. And you can see that the log function is strictly concave, so for any given tangent, at the tangent point, x minus 1 and log of x are coinciding at x equals 1, but everywhere else log x is strictly below x minus 1. So here I can write down, and this is important, that equality happens if and only if x is equal to 1. So at the point at which it is a tangent. So we'll actually show that to use this, we'll actually consider minus dpq, and we will show that it is less than or equal to 0. So we will show this. So let's write down the expression for this guy. It's minus summation over x, p of x log of p of x by q of x. When I take the negative sign inside, the log, the numerator and denominator can be flipped. So I can write it as summation x p of x log of q of x over p of x. And at this point, it's worth noting that really I'm just summing over, because I'm averaging using the distribution p, I'm really summing over x such that p of x is actually non-zero, right? So basically, I'm summing over this. I'm just noting that I'm summing over only that. And now I'm going to use the property, the bound on the log function here, this guy, and I'm going to write it as it is less than or equal to, using the fact that log of x is less than or equal to x minus 1. This is less than or equal to, and I'm continuing to insist that I remember that I'm summing over x such that p of x is bigger than 0, and then p of x times q of x over p of x minus 1, right? That's what we have. And now writing those two terms out and separating them out, the first term you can see that the p of x will cancel out and you will be left with just q of x. So you have the summation of q of x over these set of x's, and minus again x such that p of x is bigger than 0, p of x, right? And you can see immediately that a probability mass function has to sum to 1. So this is exactly equal to 1. And this is another probability mass function that I'm summing over x, but I'm restricting it to x such that p of x is bigger than 0. So it need not be all possible x. So this is less than or equal to 1. I may not be including all possible points x. So this guy is less than or equal to 1 minus 1, which is 0. So we have shown that minus dpq is less than or equal to 0, which is basically our desired result, that dpq is bigger than or equal to 0. So now let's sort of knock off when we actually have equality in this inequality. So we just have to go back in the chain of derivations and figure out, okay, in order to have equality in the final result, I gotta have equality in all the places that were inequalities. So the first place was here, right? And here I was using the x minus 1 bigger than or equal to log x inequality, and that is an equality if and only if x is equal to 1, right? So I'm applying it to qx over px. So this, let me change pen color here. This guy will be equality only if q of x over p of x is equal to 1 for x such that p of x is bigger than 0. So this gives me part of the equality condition. So this basically, if p of x is positive for all x, then I'm done, but it need not be. It may vanish at certain places, and q of x may not vanish at those places, right? So that's one condition. So what about the second inequality? Here, the second inequality says that the q of x summed over all x such that p of x is bigger than 0 is less than or equal to 1. So for that to be equal to 1, it means that q of x should be non-zero at only these places. So q of x is bigger than 0 only where p of x is bigger than 0. And these two together, you can just think about it a little bit. You can see that the equality will happen if and only if q of x is equal to p of x for all x. So again, I'm talking about probability mass functions and discrete random variables. For continuous random variables and vectors, instead of for all x, you will say almost everywhere, basically, which means everywhere where you have non-zero probability mass under the two distributions. So basically, equality if and only if Q of x is equal to P of x wherever P of x is bigger than 0, and Q of x is equal to 0 wherever P of x is equal to 0. And that completes our proof. I'm just going to put the final result in a box, and that's about all we're going to say about information theoretic divergence. It's basically the minimum we needed to prove the convergence of the EM algorithm.